Hello, good evening, my dear young innovators. Just one disclaimer before starting today's session. We are going to record this session. Hope no issues or no concern by anyone and everybody is okay with this. So with this note, as you guys are aware of, NXP, sharing new technologies to bridge the gap between academia and industry. And NXP Campus Connect is a platform where we are sharing our latest technologies, which is very beneficial for the college students. As you are aware of, on 1st of Tuesday every month we are running the VLSI track, and on 3rd Tuesday every month we are running the system engineering track. And today is the 3rd Tuesday, so we are going to share a deep dive onto a new technology, which is 5G. And we have 3 NXP experts, which is visible on the screen. So Rajan is our expert on system software, and Hemant is our expert on the 5G infrastructure software, and Pankaj is our expert on RF software. So these 3 guys are the main leaders and the backbone behind the drive of this complete software infrastructure. So without investing much time, I'm handing over to these guys so that they can sail through us that how 5G evolved and how 5G is going to be reality in near future. Over to you, Rajan.
Yeah, thank you, Manish. Hello, friend. This is Rajan Srivastav, and let's start this session. Cellular technology or cellular mobile technology, this was launched around the 1980s, and now it is 40 years or more than that. And in these 40 years, mobile technology has changed a lot. It has changed drastically where it started with in early 80s. And in these 40 years, based on the changes, generally we identify each of these 40 years decade as one generation. So in 40 years, we had 4 generations of wireless technology, and now we are entering into the 5th generation of cellular world. In this session today, we are going to have a brief walk through how this technology evolved from the first generation in 1980s, and then how it progressed in last 4 generations. 5G. Why do we need 5G technology? RF or the radio side, and its network side, how the backend network looks like. Primarily talks about protocol stack layer, and then the deployment. Any new technology that is rolled out by 5G by any mobile operator, that is very challenging. So whenever any generation change happens in mobile technology, the deployment, this transition from current 4G to 5G will happen. So now over to evolution, how this years or so. So the first generation, that was in 1980s, it was all analog. When I say analog, it was the voice was analog, and this technology was evolving parallelly in multiple parts of the world, in US, in Europe, in Japan, and each of these regions came up with their own standards, and those standards were getting popular by a lot of use by consumers, and it was an instant success. Was unencrypted communication on the radio side or on the air interface side. So one big problem was cloning. So people were cloning mobile phone, and ultimately it was a heavy loss for operators. So operators immediately switched to any alternative which could solve this this kind of phone cloning thing. So here came 2G, the second generation of mobile communication. This started in early 90s, and it introduced a couple of services, which is voice and SMS. The voice was all digital, and the signaling was also encrypted. So the two things that changed from the first generation was the encryption. So signaling was completely encrypted, and voice was digitized. And it also introduced the concept of SIM card, which using which network or the operator was able to verify whether the phone is a genuine phone or someone is trying to mimic as another user. So that SIM card was introduced in 2G. And another feature that came in 2G was roaming. In 1G, roaming was not possible. So if you purchase a phone in one city, you cannot use the same phone in another city of the same country. To make this possible, that means to enable roaming, 2G had completely overhauled the backend network. Another thing that was started coming once the people were heavily using SMS, then they started looking for some more services like email. Then some additional technologies started coming like GPRS and Edge. So those are categorized as 2G plus or 2.5G or 2.75G. In addition to GSM, there was another parallel technology, CDMA, was also getting popular in some part of the world. In India, when India started its mobile journey with 2G only, I believe 1G was not deployed in India. And in India, when we started 2G services, both the technologies, GSM and CDMA, both were used by different operators. And after the second generation, the third generation was introduced in early 2000, and the prime use case here was internet browsing. So people were able to use emails on their phone, but then they started looking for internet browsing, and that means higher data rate. So the 3G came with higher data rates with respect to 2G, 2G plus, 2.5G. And here the maximum data rate was reached up to 20 Mbps, and that was possible using some of the 3G plus technology. So 3G plus is some additional features on top of 3G. So that enabled up to 20 Mbps, but then people demanded more downlink and uplink speed. And that is how the transition happened from third generation to fourth generation. And fourth generation is also called as, you might have heard, LTE, long-term evolution, and LTE A stands for advanced. And here in 4G, we were able to get up to 1 Gbps peak data rate. And this is also providing all IP services. When we say all IP services, so browsing is of course IP services. Now here in 4G, we have even voice also on IP. That means you might have seen voice over LTE symbol on top of your mobile phone screen when you have a 4G connection. So that means your voice is also using the IP services. And now 2020 beginning, the transition has started towards 5G, where people started looking for more data rate, more download speed, more upload speed. And there was also a use case of universal connectivity. We'll talk about that more in subsequent slides. So this is the overall journey from 1980 to 2020, and this fifth generation transition is still taking place. We'll talk more about that in a while. Now, what NXP is doing in this cellular technology? So NXP is contributing in this cellular technology since primarily in fourth generation in 2010 decade. What NXP did, NXP was working in 2010s was networking infrastructure solution, what we call infrastructure in 5G. So in 5G network or any mobile network, you have a mobile phone, which is a customer side equipment, and then you see a antenna or the base station tower. Base station tower or the antenna on the top of building, you see, that is only the front end of the backend network. And behind that antenna or BTS, there are several other computing nodes that are lined up, and that are called infrastructure in this context. So NXP has designed multiple solutions to provide infrastructure. And the most prominent thing that NXP did was NXP was the first company in the world which introduced a multi-mode base station processor. What does multi-mode mean? Multi-mode means on the same CPU, you can run two or more different technologies. For example, you can run 3G and 4G together on the same processor. So how was that possible? Because the CPU can be CPU resources. When I say CPU resources, it is primarily the core, the cores, the accelerators, the memory. So all these things can be partitioned in such a way that one partition is running one cellular technology, and other partition on the same CPU is running another radio technology. So using this, operators were able to save a lot of money. Earlier, they used to have multiple CPUs installed in their backend network. Now, for multiple CPUs, they were able to use a single CPU from NXP multi-mode base station, and they can deploy multiple cell on the same hardware, single hardware. And NXP solutions were very scalable. We had multiple products where small and large cells can be integrated on the same SoC. So that was the story of 4th generation. In 5th generation, what NXP is doing, NXP is delivering software definable open networking solution. What is software definable solution? Your hardware is the NXP SoC has very flexible hardware. The accelerators and the DSP that we have are very flexible, and using software modifications, you can realize whatever technology you want to implement, whether you want to implement 4th generation, whether you want to implement 5th generation radio. In 5th generation also, there are multiple versions of the 5G releases. So using just software upgrade, you can switch to one version of 5th generation to another version of 5th generation using NXP software-defined SoC. An additional thing that NXP is working is open networking. So we'll talk about open networking in subsequent slides. And NXP products are deployed in 5G network for the infrastructure side, that is the network side, that means base station side. And NXP is also working towards the CPE side. When I say CPE, CPE is the customer premises equipment. That means you can have a 5G enabled router or device at your home to connect to internet. Today you have internet connections, connectivity at your home using DSL or fiber. So that will be replaced by this 5G CPE once you get this this product in the market. Now, let's discuss sometime why we need 5G. Okay, why this 5G was required at all, and how we will be using 5G in our daily life. So this particular slide is telling about why do we need 5G. This is primarily driven by the need for more and more bandwidth you need for downlink, for download, for upload on internet. And why that is happening? Because people are spending more and more time on internet using mobile phone. So the time spent on mobile is increasing very rapidly. The number of mobile users are also increasing rapidly, and the applications are also now asking for more and more data download and upload. Why? One of the example is the video resolution. Earlier, we used to use the standard definition HD, then came HD, then full HD, 4K. Now transition is happening from 4K to 8K. So each generation of video resolution doubles or maybe 4 times the data requirements. So to support this kind of exponential growth in data, 4G was not capable, because generally people are now looking of around hundreds of megabits per second of data rate, which is simply not achievable through existing 4G technology. Another thing that was coming as a challenge for operators, so all the operators across the world are now having a lot of pressure for revenue. These operators are making loss, and one of the biggest reason for their investment cost is rolling out the physical copper layer from their center distribution point to the individual homes. That is laying down the copper or fiber cable. That takes a lot of time and a lot of energy from the operator side, so it becomes very costly. So operators want to replace this wired 5G connection to the home. They want to go to wireless thing, so that they can save money on laying down the cable. And another driving factor for 5G is IoT devices. IoT is Internet of Things. For example, most common things are sensors, and there are several sensors that you want to connect directly to Internet. And it is expected that by 2025 we'll be having 21 billion of IoT devices, and these devices have one special thing: they are running on battery, so they really want to spend very less power on communicating to the radio interface. So to have these two things, many more devices and very long battery life, 4G is not having enough support for this kind of requirement. And the last one, which is shown on the last part of this screen, the low latency network requirement. So there are some use cases, for example, the augmented reality or virtual reality. There are games which need very quick turnaround time, and there are some use cases that are showing up now, which are shown in the right bottom of the screen, which is driverless cars. So you can see there are cars running on the road, and these cars are talking to each other, and this communication from one vehicle to other is called V2X. We'll talk about that in a short while. So these communication from one car to other, these need very low latency communication, and in existing 4G the latency is very high, which is not suitable for this driverless kind of car. So the need for supporting this kind of use case, the requirement is the network, the radio network should have very less latency, which is which should be in order of a few milliseconds. So with these requirements in background, it was realized that 4th generation of existing 4G cannot meet these requirements. So ITUR is a standardization body, which we'll talk later. So ITUR came up with 5G requirements, and this requirement is called IMT 2020. And the 3GPP, which is another standardization body, so they created 5G standards using NR, or the new radio technology. And the charter for 5G was it is shown on the right side of the screen. So it should have 10 times downlink and uplink speed with respect to the current 4G technology. The latency should be reduced by 1/10, and the spectral efficiency is how much bit you can transmit or receive using the given radio spectrum. So radio spectrum is a very costly resource. You might have seen government occasionally does a spectrum auction, and operators pay several millions of dollars on getting this spectrum. So the requirement was to increase the spectral efficiency. That means the number of bits that can be transmitted over a given radio spectrum should be 3x of the current 4G. And then other requirement for the 5G was to support 10 times more connections. This is driven because of the growth in number of IoT devices. And the last one is the new frequency spectrum. So the current frequency spectrum, which is generally from 7-8 megahertz to up to 6,000 megahertz. So this spectrum is almost sold out across the globe. And now to provide additional connectivity, additional data rates, some new spectrum is required. So that is how 5G has come up with new spectrum to support this additional bandwidth. So when the 5G framework has been created, so they created 3 different flavors of 5G, and these 3 flavors of 5G are supporting 3 different use cases. The first one is called EMBB, which is an acronym for Enhanced Mobile Broadband, and this is to support peak data rate of 20 Gbps in downlink direction and 10 Gbps in uplink direction. On average, it should be 100 Mbps data rate. And this is the most popular and most urgently needed 5G use case, and the current 5G deployment is happening on this particular use case. The other one is URLLC, which is ultra reliable low latency communication. What does ultra reliable low latency mean? Ultra reliable is whenever you transmit something, it should not be lost in the air, because you are not ready to afford packet losses. So if you can meet this requirement, the packet transmitted should reach with very high probability, then we call it ultra reliable. Low latency means that transmission should happen with whatever defined latency requirement is there. Okay, and let's take example of V2X. So if a car is running at 90 km per hour, that means in every 2.5 centimeter distance, it will be spending only 1 millisecond. Okay, that means if your network is incurring a latency of 10 to 20 millisecond as of today in 4G, so that means in 10 millisecond or 20 millisecond, the car will move 50 centimeter or maybe 1 meter distance, which might be fatal in some cases if car has to take clue from the vicinity or 5G or over the radio interface and has to apply brake suddenly. So to apply brake suddenly and to stop, the communication with the other car should be very fast, within less than a couple of milliseconds. So, and this communication from one car to other car should be also reliable, because losing the packet and doing retransmission, that is not possible, because it will increase the latency, which is fatal for a running car at high speed. So this ultra reliable low latency communication was another use case which for which 5G standards have defined some special provisions in the protocol. Then the last category of the 5G use cases is massive machine type communication. This is to enable millions of IoT devices every cell. Okay, so what is special in the IoT or Internet of Things devices? So let's take example of a thermal sensor. Suppose you have a fire sensor at some place around you. So what this fire or thermal sensor will be doing? It will be doing mostly uplink communication. What is uplink? Whenever your mobile phone or a internet device sends anything towards the network or the BTS, that is called uplink transmission. So this uplink transmission happens. Uplink transmission is the most often transmission that happens for IoT devices. Then sporadic transmission. So generally, this thermal sensor will be sending information to the network only when there is something abnormal. Temperature is really hitting very high or something like that. So the transmission will not be happening uniformly every now and then. It will be happening very rarely. Then another characteristic is this IoT devices use very small data packets. So if temperature is reaching some threshold, very small information needs to be sent by the IoT device to the network. So the data requirement, data speed requirement is very less, and power optimization for long battery life. So these IoT devices are generally packed with some very small battery, and this battery is expected to last for 10 years. So this needs to be supported by the good RF technology, because RF is very battery consuming technology. So if you have to transmit something on air interface, it takes a lot of battery consumption. So to support IoT, 5G has made some provision which expects less computation and less processing at the IoT devices. So these are the main flavors of IoT devices, 5G use cases. And we had discussed a few acronyms in the previous section of the presentation, where we were talking about multiple standardization bodies. So one is ITU, which is International Telecommunication Union. So these are generally supported by governments of various countries, and also this is backed by United Nations. These guys in ITU, they generally make a consensus among different governments on different use cases. For example, which radio spectrum to be used. Okay, what are the future technologies? For example, V2X, whether that should be covered in 5th generation. So those kind of requirement framework is created by ITU. And then there is another body which is called 3GPP, Third Generation Partnership Project. These are the guys who read the ITU recommendation, and based on that they come up with the solution. So for example, 5G NR, the new radio, that is standards were made by this 3GPP. ORAN, which is Open Radio Access Network. If you see around you, you will find base station tower or BTS. There are several other nodes also which are not visible, but those are also required for network communication. And today's very big drawback is, if a mobile operator has to purchase some technology to deploy a new network, new mobile network, they have to purchase all the node, for example, the antenna, the BTS, then the backend servers, all they have to purchase from just one vendor. So this is something which is a problem, because that creates a monopoly. So ORAN is an alliance that is creating a standard so that operators can buy BTS from one vendor, they can buy the backend nodes from another vendor. So they are making the ORAN is making the standards open. So now we are going to discuss about the key features in RF for the 5G, and my colleague Pankaj will now take you through those key features. Pankaj, over to you now. Hey Pankaj.
Pankaj, you are not audible.
Mute. Pankaj, you are still not audible.
Still not audible, Pankaj.
Not audible, Pankaj. Maybe you can try laptop's audio. No, Pankaj is still not working.
Maybe on the right hand side control panel, go to audio options on the control panel and select the computer audio. In the control panel on the right hand side of the GoToWebinar, in the GoToWebinar control panel. Still not audible.
Is it audible now?
Yeah.
It's Pankaj.
Okay. I don't know what happened. Anyways, sorry for that. And okay, so I'm Pankaj Chauhan, and I work for RF software in NXP. And as Rajan explained the use cases, We will go through in next few slides. We will go through some of the key enhancements that 5G has over LTE. When I say enhancements, these are the enhancements that we will be talking about over LTE. And then we will be touching a little bit on the millimeter wave RF that is new and the design challenges that we face because of the new features that are that have been introduced in 5G. So coming to the key enhancements, and again, I say we are talking about the enhancements over LTE. And if you ask me to summarize, this slide summarizes four key things that are new. On the left-hand side of the slide, you can see we are talking about the new RF spectrum. So in 5G, the spectrum coverage is huge, and you cover from 0.4 gigahertz to 52.6 gigahertz, and all the wireless technologies that you're aware of as of now, including your Wi-Fi, LTE, these work in spectrums which are below 6 gigahertz. And this new spectrum, which we call FR2, that is 24.5 to 52.6 gigahertz. That is an entirely new spectrum that is used for 5G NR. And for other reasons, mainly for the indoor coverage or the coverage similar to 4G, we use the FR1 spectrum, that is 410 from 410 megahertz to 7125 megahertz. So if you're using this spectrum, you will not get the peak data rates or the extreme data rates which 5G promises. So for example, if you're looking for a data rate that is about, let's say, 10 Gbps, then you have to use the spectrum in the local, you can say local area, you have to use FR2 or the millimeter wave, because in this new spectrum, you have very wide bandwidths available. The bandwidths that were there in LTE were 20 megahertz, and here we are talking about 400 megahertz of bandwidth. So the usage of the spectrum is in 5G. If you are looking for a deep indoor coverage, you use the 5G in 700 to 900 megahertz bandwidth frequencies. If you are looking for data rate which are about 1 Gbps or similar to LTE, and the coverage also similar to LTE, so that you can have larger cells, then you use for you go for this FR1 spectrum. Again, you move a little higher and you use about 3500 megahertz, which gives you similar coverage as the LTE gives you for 1800 megahertz. So we will be talking about this new spectrum because the old spectrum was already overlapped, and you might be aware of it. What challenges the new spectrum brings us, we will be talking about in next few slides. The next important thing that comes into picture, that is the second box, which is beam steering that I have shown here. It is, you can say, about 50,000 feet view of beam steering. Very simplistic, maybe kind of a nursery design, a nursery, you can say, diagram. But in this introduction, I think it is good enough. What beam steering is, you can steer the direction of the signal that you transmit and receive from your base station, the antenna that you see here, and your mobile phone or the user equipment that you have. And why it is mandatory in 5G, because when you move to FR2 or the millimeter wave, and you must be aware of from your physics classes that the propagation characteristics changes significantly when you change the frequency, right? So when you move to millimeter wave, that is any frequency that is higher than 24 gigahertz, the biggest problem that you get is your link or your devices which are talking have to be in line of sight. If you are not in line of sight, then you will have huge losses. You will not have even a link. I'm not talking about the reliable link. You will not have a link. So this calls for that if the UE is moving around, or the direction between the your base station and the user equipment is not line of sight, then there have to be a programmable way by which you can change the direction in which your signal is transmitted and received. That is a very interesting and complex kind of technology. We'll be talking about very little about it in next few slides, but it is an integral part of 5G. Coming to the third box, which is titled here as new and flexible frame structure. Why this is required? Again, this is required to realize the use cases, some of the use cases which Rajan talked about, right? That you need a very fast, you can say switching or very low latency network you need. And because of which, and also you are using a new spectrum. That when you use the new spectrum, then there are challenges like in the millimeter wave, the phase noise is really huge as compared to LT spectrum that you were using. So you cannot use the same technology, or you can not use your OFDM in a similar way that you were using in LT. For the first problem that I talked about, the phase noise, you get an option, or basically not an option, but you get a configuration that your numerology is configurable. When I say numerology, if you're aware of LT, you know that in LT you use OFDM, which uses multiple carriers or subcarriers that we talked about, we call them, right? And they are spaced. Basically, if you have a 20 megahertz LTE bandwidth, you will have multiple frequencies that you will be modulating, and each of these subcarriers will be spaced by something called subcarrier spacing. So it was fixed in case of LT. In case of 5G, it is configurable, and we have multiple options. We will be talking about that. Then you have an option for bandwidth parts. Normally, if you are talking about LTE or Wi-Fi, the devices that we are talking to each other, they use the fixed bandwidth. Either if you're using Wi-Fi, let's say if you're using 11 AC or something, right, you will be using 80 megahertz or 160 megahertz. It cannot be changed at runtime. 5G introduces a flexibility that you can change these bandwidth. Again, we will be talking about it. This helps you in a lot of things, including the power saving. Then you have something called mini slots. Again, I will not touch much on this slide about the mini slots. It changes the minimum scheduling unit that you have in the system. It is not fixed. So depending on the use case that you want to realize, you can use these slots, and we'll be talking about it. Lean carrier is something that the overheads that you have to maintain, you can say the link between your base station and the UE. The reference signals that you send, those are quite reduced in 5G as compared to 4G, and we'll be talking about that. The last box that I show here is multi-connectivity, and deliberately I have not shown it Wi-Fi here. And why I have not shown it yet, because Wi-Fi is the multi-connectivity or the interop with Wi-Fi is still not standardized, and it is expected to come in release 17 of 3GPP, right? And but still now what we have till release 16, your equipment will be basically using LTE and 5G network to best of its advantage and best of advantage of the available resources. So since the 5G is not going to replace all the network that you have with Vodafone or Airtel in one day, it will be a gradual change. So the standard provides you the way in which you can talk to both networks, still maintaining the connectivity and using them to the advantage of your use case. So that is the multi connectivity, and it is an integral part of the 5G. So that was a brief, you can say, overview, and let's move to the next page. Rajan, please help me with that. Okay, and apologies for this moving to next page message, because I'm at the remote location, so can't do that. So apologies for that. Now let's talk about the flexibility that we were talking in the last slide. And as I said, if you're aware of how LT uses the subcarriers, you have a 15 kilohertz fixed subcarrier spacing. between each subcarrier, and it cannot be changed. And in 5G, what happens is the subcarrier spacing is flexible and it is configurable, and it is agreed upon between the base station and the user equipment. And the options that you get here is 15 kilohertz, 30, 60, 120, and 240 kilohertz. You might be wondering why the hell you require so many subcarrier spacing if LTE was working fine with 15 kilohertz. The answer is that you want to cover things that were not possible in 4G. And just to give you an idea why, what happens when you change the subcarrier spacing. For example, if you have a cell or basically a coverage area which is called cell from a base station, which is not dense, right? You have people which are not too many in your cell. You can very well use 15 kilohertz of carrier spacing. But if you have as long as the soon as the density starts increasing, you will start seeing the problems, right? And you cannot have multiple devices, which is the aim of you can say 5G. So you cannot have a very dense cells in LTE, which is possible in 5G. And what you have to do is you have to move to a higher subcarrier spacing, and you move to 30 or 60 kilohertz if you have a dense environment. And now we have taken care of the dense environment. Now you might ask why 120 kilohertz, right? 120 kilohertz is required by the physics of millimeter wave. When you go to millimeter wave, the phase noise of the that frequency or the spectrum increases very significantly. Again, and apologies, I don't have a slide for that here because it will be too much detail here, but I can give you touch upon it, that the phase noise increases when you go to millimeter wave, and that's why you cannot, when the phase noise increases and your subcarriers are too close to each other, they will bleed into each other and they will interfere with each other, and you will have really bad inter-subcarrier interference that you will have, right? So when you move to the frequencies that are more than 6 gigahertz, you have to use 120 kilohertz of subcarrier spacing. There is no other option. That is what we use for millimeter wave. The spectrum that you give, that gives you 20 Gbps of promised rate. So that is the flexibility that we talked about in the how your OFDM subcarriers will be packed to each other. And when you change this, a lot of things change, and we'll be talking about it in the next slide. This calls for a lot of real-time behavior, which is driven from the frame structure that we are talking about here. And frame structure, again, I'm taking as a reference that you're aware of the LTE. And in LTE, if you remember, your frame was, or radio frame was 10 millisecond. And this 10 millisecond frame, and have a look at the left hand side, this red and orange, whatever is this color diagram. So 10 millisecond radio frame is divided into multiple subframes, and this concept wise, this remains same as LT, but due to the subcarrier spacing, things change here, right? So each radio frame is, as I said, is divided into 1 millisecond subframes, and each subframe is divided into multiple slots. And when I say slot is basically in time domain. If you see your signal, slot is a representation in time. And since we are talking about time, so slot is a combination of 12 or 14 OFDM symbols, depending on the cyclic prefix that you're using. And the number of slots that you have per subframe depends on your numerology, right? So if you're using 15 kilohertz, you have one slot in your subframe. If you're using 30 kilohertz, you have 2 slots, and it goes up to 8 slots when you're using 120 kilohertz. Now, why this is a challenge? This is a challenge because in 5G or 4G network, slot is a minimal, you can say a basic scheduling unit. When the base station gives you opportunity to transmit or receive, right? It talks in terms of slots, and then you will be assigned what symbols you can transmit or receive on, right? And if you observe that the duration of the slot length, as I have shown here, is 1 millisecond divided by 2 raised to power mu. So if the mu increases or the numerology increases towards the higher subcarrier spacing, then your slot length decreases. And for 120 kilohertz slot, your slot is 125 microseconds, and that is the time limit that you have to meet in your system at every level. When I say every level, it is hardware, software. You cannot have latencies in your inter paths or data paths which breach this minimum limit. So that increases the complexity, and I have a slide that we will talk about it. 5G also introduces a concept of mini slot, and this is an interesting concept because we talked about that subcarrier spacing was constant, but we changed it to variable subcarrier spacing. But what about if you have a UE that requires a quick turnaround for a particular use case, right? What you have to do is, because your scheduling unit, when your data transfers are scheduled, is 125 microseconds. And if you have a use case, let's say somebody is on an operating table and the surgeon needs some feedback remotely, he cannot wait for 125 microseconds, right? So his equipment needs a quick response. That's why you have mini slots, and this is configurable at the runtime, and it is agreed upon between the user equipment and the base station. So you can have 7, 4, or 2 OFDM symbols that are combined as mini slots, and your data transfers can be scheduled. So mainly it will be used when you are implementing something that requires a very less latency, or the URL, the ultra reliable low latency use cases. So that is the use case of this. With this, I think we can move to the next one. Okay. Now, remember, we had a box in the first slide which talks about the flexibility and the efficiency. And when I say flexibility and efficiency, the examples of flexibility we saw in previous slides because of the numerology and the mini slots. Few things we will talk about here also. And when I say efficiency, efficiency in both terms. Efficiency in terms of the spectrum usage, and also the efficiency in terms of the power, because if you remember the initial slides when Rajan was talking about the use cases, one of the key goals of the 5G is that to support IoT and support massive number of devices, right? You need millions of devices. And since it is IoT, your sensors will be not very, you can say, rich in power. They will be very power constrained devices. And also from the base station perspective, it is always desirable that if you don't have anything to do, go back to sleep, right? Save some power. That was not possible in LT because of the first point that is mentioned in this slide. And what 5G does to fix this is they call it lean carrier. And lean carrier, what it does is it removes a lot of overheads. And in LTE, there's a small table that talks about the comparison, right? In LTE, the base station used to send the CRS, or the cell specific reference signal, that was very dense in nature. When I say dense in nature, it was sent on every 6th subcarrier, and maximum it will be sent 4 times every millisecond, right? So even if the base station does not have anything to send or receive, right, it cannot go back to sleep. There is some, you can say, work that it has to do, and it does not know whether anybody is using or not. It is kind of a beacon that a Wi-Fi AP sends every beacon period, right? So in 5G, it is removed, completely removed. There is no cell-specific reference signal. That is the one reason why it is called lean carrier design. Then the synchronization signals by which your user equipment comes to know the parameters, right? Not the parameters, but synchronizes the frequency and time with the base station. And the frequency of these signals were every 5 millisecond in LTE. But in 5G, it is configurable. Again, by default, it is 20 milliseconds. So again, you save on power here. Same is true for the broadcast. Right? Broadcast also, the frequency is reduced in 5G. That is why it is called a lean carrier design. You can save power, and you can have UEs which do not have to wake up every 1 millisecond, right? You know that you can sleep for 1 millisecond or 20 millisecond, and if you wake up in 20 millisecond, then probably you will receive the synchronization signals. The next thing is, which is an interesting concept introduced in 5G, is bandwidth parts. And as I said earlier, that bandwidth was fixed in LTE, it is fixed in Wi-Fi, and LTE it was 20 megahertz, right? And if you are a very power constrained device, you have no option, but you have to receive your 20 megahertz signal and look through the complete band, right? And you cannot save power there, right? If you have to say, let's say, spend X milliwatt or something to scan that 20 megahertz, you have to do that. What bandwidth part does is that the user equipment and the G node B or the base station, they agree upon that. They understand that it might be required that a device might not be using all the bandwidth all the time. For example, the maximum bandwidth in FR2 is 400 megahertz, and you will not be sending or uploading or downloading a movie, right, every time. It might be something that you are taking a normal call in office, right? You are not using a huge bandwidth. So why use 400 megahertz? So that is the concept. That bandwidth part is a continuous set of subcarriers which can be set aside, maximum 4 that can be configured in uplink and downlink, and one of them can be active. So if you're not using bandwidth, go for a bandwidth part which is narrower and save power. So that is the concept of bandwidth part. Mini slots, I think we talked about in the previous slide. Let's not spend time on it. Rajan, let's move to the next one, please. Now comes the beam steering. Beam steering, first have a look at the picture on the left hand side. You see 4 squares, right? These are actually the antenna arrays, and these will be new if you have not seen the patched antenna or the phased array antenna earlier. In LTE, you know, right, there are antennas similar to your Wi-Fi router, but in millimeter wave it changes. The antenna, because your frequency is increased, so the antenna size and the spacing between them decreases, which enables us to club the antennas in the arrays like this. And the example that you here see is, if you count them, there are 32 antennas for transmit, 32 for receive in each block. And what this gives us is, this gives us the ability that by modulating the phase and the amplitude of each element intelligently. And how intelligently, probably this is not the session that we talk about it, but you can change the direction in which your signal travels. And this is pictorially showed on the left hand side. And the way it is used in 5G is that the base station, when it sends the synchronization signals, it sends, these are called SSBs actually. The SSBs are sent at a different beam direction every 20 milliseconds. And the user equipment picks one of them. And these are the wide beams, right? And the area covered is huge, but the power is less. And there is a protocol, well-defined protocol in 5G, which says that you have to scan the beams. And once you catch your wide beam, then you can refine the beams, which is shown in the second and third part of the figure. And once you have refined your beam, when I say beam refinement, that means you tune these antenna elements according to your beam width. The larger the number of antenna elements that you use, the finer the beam is, right? So when you tune it, you get the highest power and the better link. And believe me, getting this right takes a lot of time, a lot of sleepless nights, but it is really cool stuff to do, right? Okay, so, and apologies that we cannot go much deeper here, but because of the time, maybe sometime later. Rajan, next slide, please. Coming to the millimeter wave, RF, millimeter wave, as we talked about, it is 24 to 52.6 gigahertz. And what changes actually? If you have worked on Wi-Fi or LTE, then your setups are simple that if you're not using antenna, then connect the devices using the cables, but it is not possible in millimeter wave. As you saw, the antennas were stuck to my hardware, right? So all the development and the verification has to be done over the air. And this poses some challenges. Maybe you have to get your link right, and your algorithms have to adapt to the link very intelligently. Those kind of challenges that we get. And as I said, the second point says that these challenges were not there because the number of antennas were less in 4G, right? If you're using a 4x4 MIMO, you are using 4 antennas. But if you're using 2x2 MIMO, still I'm using 32 antennas here, right? Also, the beam steering is must when you are using millimeter wave spectrum because of the losses. And I'll just give you an idea of the losses. The path loss increases, as you know, the frequency increases, the path loss increases, right? Just to give an idea, the path loss for a same distance between two devices is 22 dB higher than at 28 gigahertz if you compare it with 2 gigahertz. So it is 22 dB higher, and 22 dB, you know, it is a huge amount. And not only this, your connection should be line of sight. For example, if you try to have your phone or equipment inside your house, the losses are huge. The penetration loss for a hard surface like cement, it can range from 20 to 60 dBs, right? And funny thing that will happen is, for example, if you're talking in between two devices, then let the rain come, right? When the rain comes, depending on the intensity of the rain, your loss will increase. For example, it is in one of the studies, it was like 15 dB loss if your rain is about 5 millimeter per hour, and it increases significantly if the rain increases to 50 millimeter per hour. So what it calls for is that system or the algorithms that you design have to be intelligent enough. Your link budgeting, your automatic gain control, your transmit power control have to be intelligent enough to know that these changes will happen in the environment. So that is the challenge that we get when we work in millimeter wave. And another challenge is the control and configuration I was talking about when we talked about the frame structure, right? Your slot time is 125 microseconds. So your slot times or your scheduling times are very aggressive. You must have studied the real-time systems, right? And how to implement in the operating system or in hardware. Those problems really come here when you design the 5G system, right? So you have to take actions in, let's say, 8 microseconds or even less than 8 microseconds. So it is a very tight design, but it is challenging and it is fun. So that's what I wanted to say on this. Rajan, next slide, please. I will not spend much time on this. I'll just show you these pictures. When we talk about RF, since we work in RF, I work in RF, so we have to do a lot of characterization. When I say characterization, every hardware that you test behaves differently, right? So you have to understand the behavior using your tools that you develop or the tools that are available, and then for each hardware you compensate for those defects or the impairments that you get. And a picture here is a very simple thing. If you are aware of the constellation diagrams, when we start development, we start with the left hand side of picture and we scratch our head, man, what is happening? We are not getting anything. Then we start understanding, okay, what is going wrong in the hardware, and for each hardware we try to compensate. We get to the middle picture, which gives us some relief, and finally when you reach to the right hand side, when you have a beautiful 64-com constellation, that is the place where you reach, and it gives you a satisfaction. It gives you, you can say, a sense of achievement that you were able to sail through a complex system. Okay, I'll not read through the boxes here. Rajan, next slide, please. I think we might be over time. Okay, now this is the last one which I wanted to touch upon is the challenges that you have. in the systems. In fact, you all are from academics. You love these challenges, like how to design a real-time system. So when you work in 5G, you get all those your academic knowledge, and you have to apply it in the hardware and software to realize a system that performs well in the field. And some of the challenges are real-time systems, as I talked about earlier. You are talking about you can say sub 10 microsecond scheduling time. So whether you are using an operating system that is real-time, you have to be very thorough that what you're using, what interrupts, what scheduling algorithms. So that changes a lot when you work in 5G, and you have to meet these requirements. And second point that I've written here, don't get me wrong, it really gets hot and wild. And when I say this, why I say so, the 5G NR that we are talking about, you have to support TDD. When I say TDD, that is time division multiplexing or duplexing, and where you continuously change from receive to transmit, right? And this creates a new set of challenges that were never there in Wi-Fi or LTE. Why it is a new challenge? Because you are using large number of antennas, and when you know that each antenna is supported by a power amplifier means a lot of heat that it generates. So when you switch from transmit to receive, your system behavior, your hardware behavior changes significantly. The heat and the current that it draws, the power amplifiers, large number of power amplifier draws, it changes the behavior of your system. You will see the interferences, you will see the corruptions, and you have to be very thorough with your hardware design and the software design to tackle these challenges. And the last but not the least, beam steering, we have talked about a lot, and it is kind of fun. Once you get time, please go and read about beam steering. It is really fun to do it. So that's it, and I'll hand over to Hemant for the next part of the session. Thanks, Hemant.
Hemant, your audio is not coming.
Rajiv, you are muted. Please unmute yourself.
Are you able to hear me now?
Yes,
Yeah.
Hemant.
Okay, thank you. Yeah. So typically in a given network, there is an air network. Your phone connected to your base station via air network. Then there is a access network. Then access network has a transport network which connects to the core network, and then core network connect to your respective backbone network. And if we see the 4G, the 2G started with a concept called as base station. Base station was comprising the BTS and the BSC. Multiple BSCs were connected to the mobile switching controller. Mobile switching controller were responsible for routing your calls and even connecting to the PSTN network or routing your calls to the landline network. But with the growth of 2.5G, there was also a requirement that you need connectivity not only to the voice network, but you also need connectivity to the data network. 2.5G was introduced, but it was completely revamped in the 3G. In the 3G case, your base station became a radio network controller, your BTS became Node V, and there was more focus on the packet switching rather than on the voice switching. This was further enhanced with the 4G network. The 4G network, which we also called as long time evaluation LT, the network was completely revamped. Node B became eNode B, and hence packet core was introduced to provide more and more type of services. The MME was responsible for handling the control signaling, mostly the mobile management and the session management, and the data traffic was being driven by the service gateway and then packet data network gateway, which was further connecting it to the different outside network for the IMS, internet, apps, and other services. So this is an overview how the network was looking like till the 4G time frame. And 5G, we know there is a requirement to support really large number of nodes. Like there is an expectation that in a dense area, we may be supporting up to the 1 million nodes per square kilometer. That require really overhauling of the network. And before we move into the understanding, we need to understand what are the different protocol layers. Most of you must have studied the OSI layers for a typical data network. The wireless network layers are also similar. They work on a similar concept, like one layer is responsible for providing services to the next layer. So UE represent your user equipment, a mobile phone or any other static or movable 5G endpoint network. Whatever data you want to send, it gets encapsulated through the different layers. It reaches to your G node B, which was a E node B in the LTE case. The G node B takes out the PDU part from the as part of IP network. GTP, which is a GPRS tunneling protocol, send your data under the GTP tunnels up to your core network, and from core network again the tunnel header is removed and the packets are directly connected to the core data network. 5G standard is giving a lot of emphasis on explicit separation of the control plane and the user plane messages. And if we try to look further into what actually these stack layers mean, so if we divide this into the two, one is the control plane and second is the user plane. RRC is a main block which is responsible for the system information, paging, connection establishment, configuration, handover, cell selection, mobility, as well as the measurement of your calls and reporting of your call records. And on the similar side, on the layer 3, the GPRS tunneling protocol, this is responsible for multiplexing the traffic from different sessions onto a tunnel and then sending that traffic to the core network. And if we move towards the layer 2 stack, each layer 2 stacks provide a different network interface to the next layer. Like for example, physical layer connects to MAC with a transport channel, MAC connects to RLC with logical channels, RLC connects with PDCP with the radio bearer. SDP is a new introduction in the 5G NR spec. This was not available in the LTE domain, and this is largely responsible for providing the quality of service for the data radio bearers. PDCP is generally responsible for reducing the number of bits which gets transmitted over the air interface by using the robust header compression. PDCP layer is also responsible for security of the user data as well as the integrity protection for the control data. It also helps in removing the duplicate packet and the reordering of the packets. RLC has a slightly reduced scope in the 5G NR in comparison to LTE. This is responsible mostly for the segmentation, reassembly of the SDUs, error correction of ARU. MAC or the medium access control, this is the most important layer in whole L2 stack. This is responsible for mapping between the logical channels and the transport channels, scheduling information reporting, priority handling of the UE, error handling via HARP, and the priority handling between the logical channel and a given UE. So in this slide, we have seen what are the on a high level, what are the layer 3 and layer 2 protocols. We talked about that 5G network required a really overhauling of the network because the number of node requirement became really large to support very large number of users. So the simple idea was we need to make the network decentralized. We need to go for a modular approach for the network. And another problem was till now the networks was tightly controlled by the equipment vendors, big equipment vendors like Nokia, Ericsson's. There was a need that we need to break this monopoly and we need to make this architecture as a very open architecture so that any vendor can use a top of the rack hardware and put his software and add their equipment into this network. So in order to do that, all the what we are seeing as A1, E2, E1, these are all the interfacing specs. So the interfacing spec between these layers and these network elements are being defined and they are being standardized. The interop and testing suits are being generated. So anybody can plug their network component and he can test, and it should be interoperable. It's no more a monopoly of a single vendor. The second thing which was focused in this was to disintegrate the base station, the G node V. So basically the G node V was broken into three components: CU, DU, and RU. RU, the radio unit; DU, the distributed unit; CU, the central unit, which are again broken into two parts: the control plane part and the user plane, which is a data plane part. If we focus onto the physical layer, the first thing was that we need to break the antenna related functionality. We have to move them to the radio unit. We need to move that functionality very close to your actual antenna, and we need to make sure that it is lightweight enough, because we will be deploying really large number of antennas. So it should be lightweight enough so that the processing requirement on the radio unit should be minimal. There were multiple options were considered across the whole physical layer processing. This figure represents different processing blocks of a physical layer, the layer 1. So it was finally agreed that option 7.2 will provide a best split between the antenna related processing and non-antenna related processing, and the throughput requirement over the network is also reasonable, that is 20 Gbps. We can support it by using a 25 Gbps or 2x 10 Gbps link, because anything lower will not be practical to scale, and anything above will require more processing on the radio unit, which again may not be a extendable solution. So we talked about the E node V. Typical structure was you put a single device G node V and connect it to the 5G core network. But we can break into separate parts like RU, DU, and CU, or we can deploy them as an individual component. Like RU, you can deploy multiple RUs, and each multiple RUs can connect to a single DU over the span of a 10 kilometer. The backhaul was decided as using a protocol as eCPRI. And again, you have a multiple DUs, and you can connect multiple DUs to the CU, and that can again be spread over 20 to 40 kilometers. How NXP is playing role in this? NXP is providing hardware, silicons, hardware SoCs for each of this use case. NXP has partnership with several software as well as hardware vendor. We call them as ODM or OEM, and we are even working with many tier 1 or top operators around the world who are making solutions like G node V or a fixed wireless access point or the CU, DU, or even the radio unit using NXP SoCs. NXP provide them help in using our SoC and help them in building the solution. NXP had a specialized SoC available to support the 5G and the 4G infrastructure. Like for example, this figure represents our LA1200 series of our software-defined baseband processor. Baseband represent actually layer 1 processing. This processor, you can see this has specialized general purpose 4 cores, and Vespa represent, you might have heard about the term DSP, so digital signal processing. So this present up to 16 Vespa cores, which are very efficient in defining any layer 1 algorithm you can implement using this processor. There are additional accelerators given on this SoC, like for example encoding, decoding, or connect analog to digital, digital to analog converter for connecting to the antenna interface with RF. So in short, NXP is playing a really big role in the 5G domain by enabling our partners. Till now, we have seen that as part of the deployment, we are seeing that deployment by, for example, we are all are living in India, and we know 5G deployment is not yet there in India. It will start. Will it start like in a one shot, like now you will have 5G phone and you will start using 5G phone? Typically, that's not the way it's going to work. It will be eventual. Firstly, it will be non-standard deployment, where you will be having a phone based on the network availability. It will be connected to 5G base station or a 4G base station, or connect to both, depend upon the kind of services it want to take. Eventually, when people will start moving to the more and more 5G phones, then the network will also switch. The same thing we have seen, like many of the networks have now switched from the 3G to 4G, and some of the network like Geo network, they no longer support 3G, they're mostly supporting 4G in most of the areas. If we talk about the 5G deployment, as of today, around 99 countries has the 5G services available. Mostly they are deploying FR1, which is a sub 6 gigahertz, mostly in the range of the up to 3.3 or 3.4 gigahertz range. There, and you can see this report. Like for example, this is a report from the speed test. 4G, it was able to achieve only 20 Mbps, and with the current 5G deployment, you can see there is around 9 to 10 times speed you are seeing. And similarly in upload, you are seeing around 3 to 4 times speed. If we talk about India, the 5G services are yet to start. Many operators like Jio or Airtel, they are conducting right now demos. Airtel recently conducted demo, and all of you might have read a newspaper. Government is right now considering for auction of the 5G spectrum so that the operators can start the development. So as a student, if we want to work on this kind of technology, maybe with NXP, what it mean to us? NXP is specializing in creating the SoC for such kind of services. So we need to know the system architecture design, SoC, like we can be a SoC design engineer or verification or validation engineer. We need to, on a software side, we need to understand how the CPU cluster works, DSP programming works, or the RF programming work. In terms of skills, we need C, C++, Python, real-time operating system. Pankaj talked about that how we need a real-time operating system in order to build these kind of devices. We need understanding of the Linux. Since ORN is working on the virtualized network, we need to understand how the hypervisor or virtual machine works. We need to have a good understanding of data structures, network security, as well as communication theories. There are other domains like application and field engineering, where we need to understand how to test these devices in the field, how to qualify these devices, and based on the user experience, we need to enable the customers and provide customer support. So over to you, Manish. We are done. We will be happy to take questions.
Thanks, Hemant. Rahul, do we have any hand raised or maybe any questions?
No, Mani.